Okay, so here is a problem very similar to one you've got for homework and what was exactly on the quiz. We have a board that weighs 50 kilograms, and there's someone standing on it all the way at the end. And the board is 2 meters long, and the guy is 1.8 meters away from this left edge over here. Now, we want to solve for the amount of tension in each of these ropes that are different colors, T1, T2, and T3. We can pick to pivot about any point. We could pick some point way up there, but that would make no sense to do that because it's going to make things really hard. We want to pick a pivot point that gives us the most torques that are zero, because it could be reasonable that we want to rotate about the center of mass. But then that'll zero out the torque from the center of mass of the board, but that means I'm still going to have a torque T1 here, T2, T3, and another one. So it's not the best one to do. It's certainly not the wrong one to do. It's just not the best one to do. The best pivot point is going to be what gives you the most zeros, and what gives you the most zeros is rotating about that left edge. So there are two more forces that we need to include in this diagram. Whenever you have an object that has mass and we're talking about it possibly rotating, there's a force from this object's center of mass, and this is right in the center here. So I'm just going to call this FC for force center of mass. So this is the force of gravity that's acting on this object. And we have a guy standing all the way out on the edge. So he is exerting a force as well, a force due to gravity, and that needs to be included as well. So that these forces in yellow and purple are going to cause this thing, they're going to try and get it to rotate. But we know this is in equilibrium. This board is not moving. So we really need to be able to see that this board is in equilibrium here. So when I say the sum of my torques has to equal 0, that means equilibrium. It's not moving. But I know there are still torques that are acting on this, because I know the formula for torque is RF sine theta. To cause something to rotate, you need to have some radius away from the pivot point. You need to be applying a force, and there needs to be some angle between your radius and the force applied, and that angle cannot be 0 or 180. Ideally, we want it to be 90 because the sine of 90 is 1. That's the biggest that value can be. So since we have picked the left edge to be our pivot point, T2 and T3 are not going to apply any amount of torque because they have no radius. They are applying a force right at the pivot point. So that means in the equation RF sine theta, they have no radius. So that means they're not going to apply any amount of torque. And just working my way down the line to the next force, I see force of the center of mass. Okay, that is some radius away. It's applying a force, and the angle between my radius, so I start from my pivot point, follow it out, and my force, that's a 90-degree angle. So that one definitely is going to apply some force. So I know that has to be included. And so let's do that right now, the sum of my torques. Now if I just think about FC here, if this was all alone and I was imagining pulling a rope down, that would cause this board to rotate, and it would rotate in the clockwise direction. That means that this torque is going to be negative. So this is a negative torque due to center of mass. I'll call it C there. And then I go back down my line, and I see, oh, okay, there's another force here. It is some radius away. It's applying a force, and the angle, again, is 90 degrees. So that's going to be very easy to work with. And that one too makes it want to rotate clockwise, and that is negative. So a little fancier gravity there. Let me color code that for you so it makes it a little easier to see. So this is minus torque due to Addo's gravity. And then I go back along, and I see I have a force here in red. And this force in red, it's some radius away. It is a force, and it's at an angle. Now this angle isn't 90 degrees, so we need to find the part of this angle, the part of this force that makes this want to move, that makes it want to rotate. So it has a component that looks like that, and that's Tx. And it has another component. It has a vertical component. Let's go black there. Ty. And let's make this angle 50 degrees, because I guess I forgot to say that, so let's just make that 50 degrees. So if I break this up into its two components, if I look at Tx, if I imagine pulling on a line of Tx, and I'm pulling, this thing is never going to rotate, because I'm trying to get something to rotate pulling in a straight line. That angle right here, that's 180 or 0 degrees, whatever you want to think of it. The sine of 0 or 180 is 0. That's not going to apply any amount of torque. But then, if I go and look at Ty, if I imagine applying a force in that direction, like, okay, so now what is the angle between my radius here and my applied force? Oh, hey, that one's 90 degrees. So Ty, that is the component that is going to make this rotate. And if I look at my formula, it has some radius, some force, and the angle between Ty and the radius is 90 degrees, so there isn't going to be any sine in there. The sine of 90 is 1. And if I imagine pulling on that rope, trying to get it to rotate, Ty is going to make this rotate counterclockwise. So that makes it positive, and let's go red to match it up. So this is going to be plus the torque from T1Y. So all of this has to add up to equal 0. I'm just going to move those other two to the other side. Let's extend this page to balance this equation. So I have the torque from T1Y has to be equal to the torque from the center of mass plus the torque due to gravity from Adam. And I know that torque, the formula for torque is RF sine theta, so I know all these numbers, I can plug them in. So let's look at T1Y. So T1 is a radius of 2 meters, okay, because it's all the way, it's the total length of the board away from the pivot point. And the force is Ty, or T1Y. I need to figure out what that is, because using trig, because I don't know exactly what it is. But if I'm looking for T1Y, that is opposite of my angle, and I know my hypotenuse is T1. So I know that sine theta is equal to opposite, which is T1, divided by, or T1Y, excuse me, T1Y, divided by my hypotenuse, T1. And if I rearrange that, I see that T1Y is equal to T1 sine of my angle. So I'm going to replace T1Y with T1 times the sine of my angle. And then for my formula, that just took care of my force. the sine of the angle between the force and the radius. Well, the angle between my radius here and my force Ty is 90 degrees, so I don't really need to include that. So that's all taken care of. So that, I think, is the hardest part that people struggle with, is figuring out what that angle is. And let me just plug in the number here. Let's get back to it. So it would be the sine of 50. And that has to be equal to the torque due to the center of mass, which is going to be 1 meter away, so I won't write that. And the board has a mass of 50 grams, or 50 kilograms. That's not just the force. The force is your mass times the acceleration due to gravity. So 50 kilograms times 9.81 meters per second squared, plus the torque from the ATO standing all the way 1.8 meters away. So that has the radius of 1.8 meters. That looks ugly, but that's okay. Times the force he's exerting of 1,000 newtons, and I'm running out of room here. But I trust you guys can all figure out what's going on. So this equation, I have one unknown. I just don't know what T1 is, because 2 is a number, sine theta. These are all numbers. And if I plug this in, so 50 times 9.81 is 490.5 Newton meters. Just remember we had 1 meter in there. And then 1.8 times 1,000, that's some difficult math, 1,800 Newton meters, is equal to 2 meters times the sine of 50. So 2 times sine 50 gives me 1.53 meters multiplied by T1. So, and then solving for T1, so 490.5 plus 1,800, and then that gets divided by 1.53. T1 is equal to 1497 newtons. And if you remember, that's a much bigger number than we solved for in the quiz. And yeah, that makes sense because this board has more mass, ATO has more mass, he's standing farther away. So this torque from him due to the his force of gravity, he's a lot farther away from the pivot point. And we know torque depends on your radius, your force, and angle. If he has increased his force, he is going to increase the amount of torque that he is exerting. So that is T1. And then to solve for T2 and T3, let's extend this page, we'll run through this real quick. What color did I make that? Blue. For, well, let's do T3 first, actually. I think I made that green. Yes. Okay. So T2 and T3 aren't exerting any torque. We've already gone over that because they have no radius. But they are still forces. So we can do Newton's second law that says the sum of the forces is equal to mass times acceleration. T3 is acting in the x direction, so we will do the sum of the forces in the x direction. And hey, this board is not accelerating in the x direction at all, so this is 0. But there are still forces acting on it in the x direction. There's T3 and the T1x, this x component from T1. So we'll just say, all right, moving to the right is positive x and up is the positive y, just our normal convention. Plugging this in really quick, that means that T1x minus T3 has to equal 0. T1x is equal to T3. T1x, you need to be able to see this, is equal to T1 times the cosine of theta, so T3. you need to be able to figure out how we get that, and then we just plug that in. So T1 we already know is 1497 times the cosine of our angle, which is 50, so that T3 is equal to 962.3 newtons. So we have that part. Then the final part we'll solve for T2, which points in the vertical direction. So let me extend that page. And again, we know T2 is not applying any amount of torque because it has no radius, but it's still a force. So we can still do Newton's second law in the y direction equals, or causes our mass to accelerate in the y direction. But our mass is not accelerating. It's not moving at all. So I know this is 0. But I still need to include all of my forces that are acting in the y direction. T2 is positive, and T1y shows its head again because it is pointing in the positive y direction. So we have to include that. Then we're going to have to include the force of the center of mass and the force due to gravity, because those gravity points in the vertical direction, and those are both going to be negative because they point down. So force center of mass minus the force due to gravity, all that has to equal 0. And I'm going to solve for T2, so I'll move all that over to the other side so that T2 is equal to the force from the center of mass plus the force due to gravity minus T1y. One mistake I see people run into here is they're so stuck in like the rotational mindset and talking about torque that they'll try and include a radius in there. And we don't want to do that. We're talking about forces. So that's why I try and make torque look really fancy, and tension, which is a force, make it look less fancy. So plugging this in, T2, the force due to the center of the mass, that is the mass times gravity, times 9.81. And then the force due to gravity, that was Atto's 1,000 newtons. And then minus T1y, and T1 was 1497 newtons, multiplied by our sine of our angle, so sine 50. And again, you need to know how T1y is equal to T1 sine theta. So adding, all of that together, so this was 490.5 newtons. And excuse me, this should be a plus sign right there. That wouldn't make one sense. So plus our 1,000 newtons, 1,000, there we go, minus 1497 times the sine of 50 minus 1146.8 newtons. So we're going to get 490.5 plus 1,000 minus 1146.8. We get that T2 is equal to 343.7 newtons. And that's a lot less than T1 or T2 or T3. But let's look at our picture up here. If we think about it conceptually, we're putting a lot more stress on T1 over here because we have 1,000 newtons of force that's acting so far away from this pivot point that T1 needs to take all of this force to be able to balance that out. And T1 points in a fairly vertical direction. It's above 45 degrees. So that there is not, T2 over here doesn't have to do as much pulling in the vertical direction to help maintain this balance. But we see that T3 has to do a lot more because T1 points in such a vertical direction. Alright, so I hope this helps you out. Watch this video and we'll work something out with your quiz grades because I know you guys are all concerned about that. Alright, enjoy the Super Bowl. I'm going to make a prediction 28-24 Carolina.